प्यारे बच्चों, today we will start op-amp based RC phase shift oscillator, and we will derive frequency of oscillation for phase shift RC phase shift oscillator using operational amplifier. Op-amp based means for basic amplifier we are using operational amplifier as the base amplifier. And so basic amplifier is used here in inverting mode. So this is the operational amplifier. Obviously non-inverting terminal is grounded, and at the feedback we are using combination of RC network. So this is the RC phase shift, and here output of feedback network is connected to the input of the operational amplifier. Here we are using two resistances. Suppose these are two resistances used in operational amplifier. Capacitance and resistance, combination of this. So output of this operational amplifier is the input of this feedback network. This is the feedback network. This one is the feedback network. Output of operational amplifier is the input of feedback network, and output of the feedback network is the input of this. So suppose here this is the feedback signal PF at the output of RC. So what is the value of beta? Value of beta is the output of feedback network to the input. If this is the input of feedback network, then this is given by PF upon P. So now we will derive frequency of oscillation for this. To derive frequency of oscillation, we will draw an equivalent circuit using feedback network. So feedback network is a combination of three-step RC network. So 180-degree phase shift, because we are using inverting amplifier, 180-degree phase shift is provided by op-amp, and 180-degree phase shift is provided by RC network. That's why in total phase shift in closed loop is 360, which is the basic condition for oscillation. So see here, equivalent circuit. Now we are running a circuit here for frequency of oscillation. First draw feedback network, which is combination of RC. Suppose this is the input. If here we are using VI, capacitor, resistor, and assume that three currents are, loop currents are I1, I2 and I3, then this voltage is the feedback voltage and this is the input. We have to calculate this VF upon VI. To To find out, first apply KVL for three loops. In first loop, in frequency domain, we are writing current in first loop plus total impedance in the first loop, that is 1 upon this. This is the common branch, common resistance between first and second loop. Then we can write minus I2 into R. There is no common element between first and third, therefore no element of I3, and this is equal to Vi. This is the first one. For second one, this is for loop 1. For second loop, common element is R, that's why it's minus I1R plus total impedance in the second loop, that is 2R plus 1 upon SC into I2 plus common element between 2 and 3, that is, and this is common, that's why we are writing minus I3R. This is equal to 0 since there is no active element in the second loop. And third one, this is 0, only common element is between 2 and 3, therefore we are writing here, you can write I2 first for similarity. This is minus I2 into R, and for third, total impedance in the third, that is 2R plus 1 upon C into I equals 0. This is the third. So these are three equations for three loops applying KVL. From this we have to calculate this. And what is value of this voltage? This is simply current into resistance, that is I3 into R. This is the drop across R. So current in this element is I3. So drop is I3. So we have to calculate I3. And to find out I3, delta 3 or delta, we will use this. You can apply matrix to write these three equations. After writing in matrix form, we can calculate these two determinants, delta and delta 3. Then from that, we can calculate I3. So now we will write matrix form, then we will calculate this I3. So procedure is very simple. So in matrix form, suppose we are combining these equations in matrix form here. From first equation, this is the R plus 1 SC, you can write this is 1 plus SCR upon SC. Coefficient of I2, that is minus R, and coefficient of I3 0. And second row, coefficient of I1 is minus R, coefficient of this is 1 plus twice SCR divided by SC, and coefficient of I3 is, this is minus R. From third equation, coefficient of I1 is 0, coefficient of I2 is minus R, and coefficient of I3 is 1 plus 2 SCR divided by C. So from this, and this is the coefficient I1, I2, I3, our matrix. And in right hand side, coefficient of right side, from first equation it is Bi, from second it is 0, from third it is 0. So this is the matrix form of these three equations. And now from these three equations we can calculate, to calculate this which is I3 into R. So first you have to calculate I3 which is delta 3 upon delta. So now what is value of delta? Delta is simply this value. In determinant form, this is 1 plus SCR upon SC minus R 0 minus R 1 plus twice SCR upon SC minus R 0 minus R 1 plus 2 SCR divided by this. So this is the determinant, and this is assignment for you. Solve for this. I am writing directly. After solving this determinant, you can write you can expand this determinant in terms of any row or column. This simple mathematics, expansion of determinant. So I am writing directly. You have to solve this. From solving this, this is 1 plus 5 SCR plus 6 S square C square R square plus S cube C cube R cube whole divided by S cube C. So this is solution of this determinant. After solving, you have to solve this determinant. You can expand in terms of first row. So this element into cross multiplication of this, then minus this cross multiplication of this, then in terms of 0. After expansion, you will get this. And second thing is we have to calculate delta 3. Delta 3 is this determinant. You have to replace this last third row by right side row. That is, this determinant is given by SCR upon SC minus R 0. Second column minus R 1 plus 2 SCR minus R. And third column is replaced by right side, that is VI 0 0. So this is the delta 3. Only last column is replaced for delta. If delta 2 is required, then we will replace second column. If delta 1 is required, we will replace first column. So for delta 3, you have to replace third column by right side. After expansion, again I am writing directly. You have to solve this determinant. This is not matrix, actually this is determinant. So after solving, you will get delta 3 as VI R square. This is very simple because some terms will become 0 due to this third column. So expansion is very simple for this delta 3. Now come to I3, which is delta 3 upon delta. So what is this value? Simply put these two values, you will get VI R square cube C cube whole divided by 1 plus 5 SCR plus 6 S square C square R square plus cube C cube R cube. This is the expression for I3, which is obtained from delta 3 upon delta. Simply replace values of delta 3 and delta, you will get this value. Now you have to calculate V0, which is Vf obviously this is I3 into I, because voltage is obtained by this equation. So you know I3, simply multiply by R, you will get voltage. So this is very simple. Simply multiply this. Now R cube. So you can write like this is Q CQ R cube. Due to symmetry, you can write like this. 1 plus 5 SCR plus 6 S square C square R square plus CQ R cube. So this is the output voltage. Now we have to calculate this. So this is also very simple. And you will divide by VI. You will get this S cube CQ R cube 1 plus 5 SCR plus 6 plus now from here we have to calculate frequency of oscillation. Now frequency of oscillation. To calculate frequency of oscillation, put S equals J omega in above expression. You will get beta equals. So obviously when you will put J omega, square terms mean J square minus omega square, and cube term will become minus J omega because J square equals minus 1. You will get all these three terms. So replace these three values. At the place of S cube, this. At the place of S square, put this. At the place of S, put this. So you will get, this is minus J omega cube CQR cube in numerator 1 plus 5J omega C. This is the first term. This is minus 6 omega square C square R square plus, at the place of this you will get minus J omega cube CQ R cube. And from here we have to proceed for frequency of oscillation. To simplify, rule is simple. First we will separate real and imaginary part, then we will put imaginary part equal to 0. So after why we have to put imaginary part 0? Because total phase shift is 180 degree. To obtain this, suppose any complex number is represented by this, then what is the phase? Phase is given by y upon x. So to get phi 0 or 180, imaginary part equals 0. When this is 0, you will get phase 0. So phase, to get 180 degree phase shift, imaginary part of this is 0. So we will separate into two parts, real and imaginary part. So beta. So divide this whole term by this numerator. So in numerator you will get 1. When we will divide this whole expression by this, means numerator and denominator both are divided by this term. So in numerator you will get 1, and in denominator at this place you will get 1. We are writing last term first. Here at this place you will get 1. And what about this? Then you can write here square term is there, then you can write minus 6 upon j, that is plus 6, okay, upon j, you will get omega CR, no, this is square, this is cube, so upon j, 6 upon j omega CR. This is for this term, and for this, when this is divided by this term, you will get a square in denominator, because here cube and omega c are there, j is cancelled out, you will get minus 5 upon this, that is omega square c square r square, and at the place of this you will get minus 1 upon j omega cube c cube r cube. So now from here you can write beta is 1 upon. Now put for simplification, alpha equals this term, omega CR. Then beta equals 1 upon 1 plus 6 upon j is 6 alpha upon j minus 5 alpha square, and that is minus alpha cube upon j. Then we will replace, you can this write 1 upon, you can separate real and imaginary parts, 1 minus 5 alpha square, this is real, and these two are imaginary parts. You can multiply j from numerator and denominator, you will get here j upon j square, that is minus, here this is the plus, so j square, that is plus j alpha cube minus j upon j, that is j square minus 1, so minus 6 alpha. After these two terms are, and beta equals 1 upon 1 minus 5 alpha square, this is the real form, you can take common also, this is alpha square minus 6. So this is the expression for beta, and we can easily obtain frequency of oscillation from this expression. Putting to get 180-degree phase shift, imaginary part equals 0. That is this part alpha, this is 0 means, since alpha is not equal to 0, therefore we can write alpha square minus 6 equals 0, and this implies alpha square equals 6 or alpha equals under root 6, and from here we can write expression for frequency of oscillation. Alpha equals under root 6, that is 1 upon omega CR. This is under root 6. And from here, we can write omega equals 2 pi f. This is under root 6. And from here, frequency of oscillation is 1 upon 2 pi under root 6, or even CR under root 6. So this is the expression for frequency of oscillation for RC phase shift oscillator using operational amplifier. 1/2 pi CR total 6. So this is frequency of oscillation. Now you can get condition also. What is the condition on beta? Because expression of beta so this is the expression for frequency of oscillation. Now condition on beta and A gain. So what is expression for beta? Beta is this. Again I am writing this expression 1 minus 5 alpha square, this is the real part, plus j alpha square minus 6. This is the expression for beta. And at frequency of oscillation, when oscillation occurs, imaginary part 0, that is this part is 0. So for oscillation beta is this simply 1 minus 5 alpha square. This is the, and you can put value of alpha square. Obviously from that expression you have alpha square equals 6. Therefore you can write 1 minus 5 into 6, that is minus 1/29. So magnitude of beta is 1/29. This is the value of beta. And what about A? Since A beta is greater than or equal to 1, this is the condition. And from here, when magnitude of beta is 1/29, you can say magnitude of this is greater than or equal to 1. So magnitude of A, this must be greater than or equal to 29. So this is the condition. Okay. So basic amplifier, which is our operational amplifier in inverting mode. So gain of that amplifier must be greater than or equal to 29. And this gain can be achieved by varying resistances of output, that is Ri and Rs. So this is all about operational amplifier based RC phase shift oscillator. So rule is simple. First draw the circuit of oscillator, then draw an equivalent circuit to find the frequency of oscillation. Simply apply KVL for 3 loops, write equation in matrix form, then calculate beta and put imaginary part equals 0. Okay, thank you. This is all for today. Thank you.